So the internet is flaky, so we'll see if it can get through this talk. So as Jake so eloquently mentioned, I am Safia, and I'm here to talk to you about memory management in JavaScript. If you're sitting in the back or you can't see the screen or for whatever reason, you can follow along with the talk at j.mp/js-mem-live, and you'll just automatically see everything, but also the internet is down, so you can't. It's not moving. I'm sorry, guys, this is no fun. It's reconnecting. Oh, this is so awkward. Oh my God. I'm not worried. I could do this thing just without slides, but that wouldn't be fun. Oh, shucks. I actually can't do this thing without slides. Yes, do we have Ethernet? I could tell jokes in the meantime. Knock, knock. King Tut. Kentucky Fried Chicken. What does a web developer's ghost say? Twitter bootstrap.
I was going to come on stage and help, but you've got this, right? Whatever.
The faster he works, the quicker this torture will be over. Let's see if I can remember another one. Oh God, I can't.
Don't even have any good memory banter. What's your favorite memory address?
Oh my God. Putting me on the spot here.
So have you been able to use the Chrome's DevTools in terms of memory cleanup?
Yes.
You are the only person in the world who can use that. That's amazing.
And believe it or not, once this is set up, you guys are actually going to be getting the opportunity to interact with the Chrome DevTools a bit more. I created a tutorial, an interactive tutorial for everyone at the conference to follow along with to learn how to use DevTools.
I always find that that's one of the reasons that I kind of stay away from like the kind of single-page app push state stuff, because I think no matter how bad I handle memory, I know I'm one navigation away from it all being cleared and starting again.
Yes, you're good. Yeah. Awesome. Okay, we're
right,
back.
I'll go away. Bye-bye.
Okay.
I hope it's my network, so...
Okay. Awesome. So I'm Safia, as I already mentioned. My two passions in life are data science for social good and open source software. And if you're interested in learning more about that or the open source work that I'm doing, I'm Captain Safia on Twitter and GitHub and NPM and like MySpace and Friendster and all the stuff. And Safia.rocks is my website. So what are we going to be talking about today? And I just want to give you a quick outline of what you guys are getting yourselves into. So first, I'm going to talk a little bit about why we should care about memory as software engineers. Whether you're working in the client side with JavaScript or the server side, I'm going to give you reasons to think about memory first. And then we're going to talk about what it means to manage memory. And for those of you who might have computer science degrees, this is going to be a throwback to your systems or compilers courses. So I'm sorry if I'm bringing up very horrifying flashbacks right now. Please bear with me. And then we're going to talk in particular about how JavaScript manages memory. And then we'll finish it off with how we can write memory performant applications. What are some tools and techniques that you folks can use? And once all that is done, you will be wizards and witches of JavaScript after battling the Dark Lord of memory leaks. So first, why do we care about memory? Why is memory important to us as programmers? And these are three very biased reasons that I have for caring about memory. The first is that it forces us to be more inventive programmers. I always think it's great to add restrictions to the way that we develop our software because it forces us to reason critically about our applications, to analyze and debug things and use tools like the Chrome DevTools, and to build better. There's no way to get somebody more creative and inventive than by locking them in a dark room or by placing them in the middle of the Sahara in 113-degree weather with no Wi-Fi and having them code. Ask me about that later. Memory is scarce, and although the amount of memory that's available on machines has been increasing over the past couple of decades, so have people's expectations of what their machines can do. Your users expect your applications to be able to handle their multitasking workflows. Users expect and deserve really rich, interactive web experience, and those things tend to be really memory intensive. And then finally, it helps us exercise our empathy muscles. I view empathy as a muscle that you can train. And thinking about the different conditions that your program is going to be used in or your application is going to be used in the context of memory is a really great way for you to discover new user stories and start to think about how your application is being used. So now that we have a couple of reasons to care about memory management, let's go a brief overview of what memory management is. So if you programmed in C, you are familiar with a paradigm known as manual memory management. And what that means is that you as the programmer had to allocate memory on the machine using malloc. Then when you were done with it, you were responsible for freeing it using free. Now, there's a fundamental issue with that, and it's that this is a huge cognitive load on you as the engineer. You can imagine, in addition to having to hunt down missing semicolons and arguing over where you place your curly braces and thinking about algorithm design and software architecture, you have this additional cognitive load of managing the memory of your application and actively thinking about it. So you can imagine software written this way has lots of memory leaks, has lots of other memory-related bugs. No fun for anybody. And that's where the concept of automated memory management comes in. It's known as the garbage collector. This is Oscar the Grouch from Sesame Street. And the garbage collector is really in charge of finding out where garbage memory is and then clearing it away. And we'll get into that a little bit later. And automated memory management has its pros and consequences. The first big pro really for us as engineers is we don't have that cognitive load of having to manage memory on our own. The big consequence is that the garbage collector is an application. It's another program that runs in order to clear your memory, so it does have a performance hindrance. And depending on how good your memory allocator is and what technique it's using, that hindrance might not be as bad. That is still a consequence. Awesome. So now we talked about memory management, and we're going to cover it in JavaScript really quickly. Is everyone with me so far? Oh yeah. Get hyped. So for the rest of this talk, I'm really going to be focusing on the V8 JavaScript engine. We're all pretty familiar with it. If you use Chrome, that's the thing that's interpreting and executing your code. If you're using Node or MongoDB on the server side, it's responsible there. So sorry for all the other JavaScript engines who won't be getting any love from me today, but V8's where it's at. So let's start off by going through the basic data types in JavaScript. I'm going to start off really easy and then ramp it up super fast. So you have your booleans, right? Your trues, your falses, your numbers, your 1, 2, 3s, and you have your strings, your hello worlds, and your nyan cats and all that. And all of these are the sort of elements in the JavaScript universe, and they can be combined to form different compounds and molecules in your application. These are really the basics. And where that becomes relevant is how memory is allocated. Memory is allocated in a heap structure. So it looks something like this. So the red node you see there is the root node. This is something like the window object. The root node has edges pointing to other nodes, in this case the blue nodes and the green nodes. The green nodes in this particular case are your booleans, your numbers, and your strings, those fundamental elements. And the blues are references to those things. So this is what memory looks like. It's essentially a giant heap, which is why Jake made that joke earlier. And V8 does something where it allocates memory into 6 different spaces or chunks. And there's sort of a method to the madness of why it does this, and we're going to find out why later. I hope I'm keeping you on the edge of your seats with all this, like we'll find out later, trying to keep you guys excited. So let's talk a little bit about these different kinds of spaces. So the first space is the new space. This is where memory gets allocated when an object is immediately created. Objects in the new space tend to be smaller, they're newer. It's a new space. Your next space is the old pointer space. So if an object is in the new space and it's a reference to an object, it's not a scalar itself, and it's resided in the new space for a while and it's been actively used, it graduates to the old pointer space. And if it's not a reference, the scalar graduates to the old data space. And then you have the large object space. This is where you store giant lookup tables and things that you don't want to fall under the memory restrictions or the size restrictions of the new, old, and of the new and old space. And then you have the code space. The code space is special because it contains executable memory. Memory on your machine by default is not executable because you don't want to go around just running whatever data is on your memory. That would not be good. And so items in the code space are generally gitted instructions, just-in-time compiled. And then the last space is the map space. And this contains maps, property cells, and cells. And these are used by the JavaScript engine. And really, for the rest of this talk, we're going to focus on 2 spaces, the new space and the old space. So you can just kind of forget about the rest, and you can treat it as like fun stuff you learned. So at this point, we've allocated objects in memory. They're in our heap. How do we know what to clean and how to clean it? And really, the answer and the basis for this is reachability. Memory is considered garbage when it's no longer reachable or accessible in your code. This usually tends to be data that is not reserved for local variables or function parameters or global variables. If you look back into the heap, the way that we can determine what is considered garbage is by traversing through our heap. So if you start off at the root node, anything that you can access by traveling through nodes in the heap is considered accessible and reachable. Things that you can't access are not reachable and they're garbage. So these 2, you're out, garbage. But how exactly does JavaScript collect garbage, or the V8 engine collect garbage? We know how it allocates memory, we know what it considers garbage. How does it collect it? And the V8 engine employs something called the stop the world technique for garbage collection. And so what happens is programs halted, like complete stop. And then there's a pause. And in that pause, there's a moment where the garbage collector runs. And it's a brief, short cycle. And that's really to offset that performance hindrance. So you're just running quick garbage collection cycles in pauses in between your program. This next GIF is going to be a perfect representation of what this means. Yes, we've all seen this. So if you remember earlier, we talked about the new space and the old space. And so when you start to go through these garbage collection cycles, the V8 engine has different approaches to how it collects garbage in the new space and how it collects garbage in the old space. So we'll start off by talking about how it collects garbage in the new space. And before I go there, this sort of idea of having a different garbage collection approach to old memory and to old data versus new data is known as a generational garbage collector. just think you're kind of like approaching the age of your memory in generations, and you're treating each one differently. And so let's talk about how garbage is collected in the new space, and it's a process known as scavenging. And so generally, memory in the new space is collected more quickly than memory in the old space, just because it's newer. And what tends to happen is when your new space is filled, the V8 engine's going to go ahead and start a scavenging garbage collection cycle in the new space. And what happens in the scavenging process is your garbage collector is going to go through your entire heap. And it's going to traverse it, starting from the root. And it's going to make copies of everything that it traverses. And then it's going to clear out what was previously in the new space. And so the copies it has made is everything that it could reach in a traversal of the heap. And everything that it couldn't reach and couldn't copy is considered garbage memory, so that's okay. Now, for those of you who are paying attention to how this technique works, you might realize the fundamental problem with it, which is that it has a very high space complexity. You need to have double the amount of memory that is the size of your new space for that copying over. And this might be a kind of consequential thing, but as if you recall, the data in the new space is younger, smaller data. So this sort of fact that you need double the size of the new space is not that big a deal. So if we go back to our lovely memory heap, we're going to start off at the red root node, and then traverse over to the blue, and then go over to the two blues, and then go over to the greens. And our garbage nodes are never traversed, and they're never reached, and they're never copied over, and they're just like obliterated into nothingness. And then for the old data space, there's a different technique that gets used, and it's the Markandsweep technique. And the Markandsweep technique works by traversing the nodes in the heap, marking the ones that are active, and then removing unmarked objects on a regular basis. And I know that was a super cryptic description, and I could bore you guys right now with an entire discussion on Markandsweep, but I want you to stay my friends. I really hope you do, so I won't torture you that way. But in all seriousness, Markandsweep has a very rich history in computing, and it merits its own 30-minute, maybe 45-minute talk if the organizers will let me. But if you guys just want to grab me during lunch, maybe do it tomorrow because I'm still jet lagged. But yes, I'm happy to talk about it. So at this point, you're almost masters of memory management in JavaScript. You have an understanding of why we care about it, what memory management is in a general perspective, how it works in JavaScript, how the V8 garbage collector works. Now you want to start to apply these. And really the best way to approach this is to start by asking yourself two simple questions, which is, how much memory is my application using? And you're never going to get a solid quantified answer for this, because that's not how it works. But you can start to develop ranges. You can start to develop metrics with how much memory you're comfortable with having your application use. And when you develop these metrics, it's important to consider that your application runs in the context of other applications. So all 8 gigabytes of memory or all 4 gigabytes of memory on a machine don't belong to you entirely, which is sad. You're sharing these with lots of other applications. If you've seen people use 48 tabs in their Chrome browser and you're like, why do you torture your browser like that? You have to share memory with all of the other tabs that they have open. And the second question that you want to ask is, how often does the garbage collector cycle in my application? How often does it run? And you can actually find this out. I don't have pictures of it in my talk, but if you use the Chrome DevTools timeline tab thing that shows all the stuff that's happening in your application, Jake will explain later, you can actually find when garbage collection cycles are running in your application. You can determine how frequently they're occurring. That might be symptomatic of how fast stuff is allocating in the new space. So if you're like aggressively allocating new memory in a loop or something like that, you might want to optimize that. There's like stuff you can do. That brings us to the right tools for a really messy job. Debugging memory is no fun. Like, I'm surprised most of you are still engaged in this talk. Way to go, good job. But good tools can make it much easier. And so the first awesome tool is, once again, in Chrome DevTools. There's tons of awesome tools in Chrome DevTools, mostly because the folks at Google are building lots of very memory-intensive applications, things like Gmail, things like Google Drive. And so, you know, if the Google Drive team or the Gmail team is like, we need tools to debug or figure out memory in our applications, they'll go bug the Chrome team, and the Chrome team will be all like, all right, we're at your service. And so the result is that there's a rich tool set for inspecting heap allocation and for examining and profiling our applications in DevTools. Yay, that's great for us as programmers. And so this is a snapshot that I took of the Chrome DevTools heap allocation profiler running on the Facebook web application. And there's sort of two curious things that I want to point everyone to, which are the retained size and the shallow size of an object. And you'll see these mentioned a lot when you start to independently research memory management, because I got you so excited about it. The shallow size of an object is the amount of memory that it holds in and of itself. And the retained size is its size and all of its dependents. So if it's pointing to anything in the heap structure, it's all of those. And the Chrome DevTools allows you to see that. Oh my God, there had to be an npm command in this after Luri's talk. Yay! Another great thing about having tools like npm available to us is that people can build utilities to help other programmers do their stuff and things better, and so we're all happy people. And the particular utility that I want to showcase here is called heapdump. Heapdump is a JavaScript library that you can install for Node, and it allows you to take a snapshot of your heap at a particular instance. And it's a super easy to use library. It's got a very simple API. There's only one function that it exports, which is write snapshot. What you can do is you can take a snapshot of your application at a particular instant, and you'll get a file with a .heap snapshot extension, and then you can actually load it into the Chrome DevTools profiler and start to analyze it inside that really awesome interface that the team at Chrome built. Instead of reading the raw heap snapshot file, don't do that. That's not smart. Spare yourself the trouble. Awesome. So I'm going to try and stay on time here with 4 minutes left. I mentioned that I put together a resource for everyone here today that I will show off now. Awesome. Okay, hopefully everyone can see this. Awesome, so this is just an interactive experience that I set up. And it starts off with the very basic console logging things. And you start to get familiar with the heapdump tool and writing snapshots, and there's some questions for you to think about. This is basically a homework assignment, so I'm like your college CS professor that you hated, but hopefully funnier. So I'm going to go ahead and publish this really quickly. Let's hope it works. Awesome. And I'm going to live tweet it out. Awesome. So this way you guys will be able to see. I can't live code in my presentation, so the least I could do is live tweet. That'll help, right? Awesome. there's probably a typo in that, as is there a typo in all my tweets. Thank you for the applause. I know that was, all of computation led up to that. Awesome, so feel free to check out that tool. There is a link to the GitHub repository for it, so if you have trouble with it, or like you're confused by my directions, or you think there should be more jokes in there, just open up an issue and I'll address it. If you want to get the slides for this talk, they're available at safia.rocks. There's a talk section on my website, and if you scroll down, you'll see all the good stuff. And finally, thanks for being a wonderful audience. Thanks to the organizers for putting this together and for like bringing us all here. I'll try and get a lot of sleep tonight so I can like actually communicate and interact with you people without being jet lagged and insane. But thanks. I hope my talk was like super informative and you took something away from it, or you just like liked my jokes. That's fine too. I'll stop talking now and Jake can come up and he'll say.